Okay, here we go. All right, I'm just going to go through the topics and things that you need to know, and I'm going to do examples along the way. Let's start with, I'm going to do page 390, number 4, and it says, that the velocity is given by the function 6t squared minus 18t plus 12, and it's going from 0 to 2. So this is the function. It's a velocity function of a particle moving along the x-axis. Use analytic methods, which means not your calculator, to do each of the following. The first thing we want to do is determine when the particle is moving left, right, blah, 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 blah. You know, actually, this is what I'm going to do. We're going to go, let's find the displacement. So displacement is, that's really nice writing. Displacement is the integral of velocity. So to find the displacement, you're going to integrate 6t squared minus 18t plus 12, and we're going to do it from 0 to 2, since that's the time that was given. And then that, of course, is a reverse pop and drop. So what is that? 2t cubed minus 9t squared plus 12t, and we're evaluating it from 0 to 2. This is if you had to do it by hand. If you're allowed to use a calculator, then you're just going to do FN int, right? And you end up with, your answer ends up being 4. So that's your displacement. So, and I can't remember. I have a feeling that you are allowed to use your calculator, but you've got to set up the integral, I think is what you have to do, but I'm not 100% positive. If we ask you for the final position is the starting position plus the displacement. And in this case, you need to figure out let's see, final position. Oh, okay, so the directions say find the final position if so this is given that if S of 0 equals 3. So that's your starting position. That's the starting, since they're telling you the position at time equals 0 is 3. So the final position will be 3 plus the displacement you just found, which is 4, and so the final position is 7. And then if they ask you for, so here's, I'm just going to call it A, B, C. It may not match up to the book's directions, but we don't care. You care about what you're going to see, right? What about total distance? So remember, displacement is how far from the original spot that you moved. Total distance is something different. That's when you're going to integrate the absolute value of velocity. If you think about it as your displacement, if I were to leave home, go to work, and then drive to work, and then drive back home, my displacement is 0, right? I'm starting at the same spot I started. That's displacement, how far away from your starting position. But that doesn't mean I didn't travel a distance. Of course I did. I traveled the distance from my home to school and then school to home. So that's the difference between displacement and distance. And in this case, you're going to go and integrate the absolute value of the whole 6t squared minus 18t. You're doing the absolute value of it this time, right? And you're going to definitely do FN int on that one, and this ends up equaling Sorry, I squished that all into the one slide, but there you go. So given a velocity function in times, find the displacement, find the final position given a starting position, and then also find total distance. So you'll have to do that. I think those were on the quiz also. Next, let's do same page, but number 21, where it gives you a rate, right? It says the rate of consumption of oil in the U.S., blah, 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 blah. So the rate is given by this function, 27.08 times e to the t over 25, where t is the number of years after January of 1980. Find the total consumption of oil from January 1st to January of 80 to 90. All right, so here's what you need to know is that when you integrate a rate, it gives you a quantity. And so if they're giving you this rate and they're wanting to know how much oil consumption, this is the rate, you're going to just integrate it, right? And they want it from, it says T is number of years after January of 1980. Jeez Louise, this book is old. I don't think it's that old, but that's old, whatever. And they want the consumption from 1980 until 1990. And so what you're going to do is integrate until 1990. That means your T would be 10. Yeah, so this is from 1980 till 1990 means you're going to go from T is 0 until T is 10. And then you're going to just integrate this rate, 27.08 e to the t over 25 dt, and then you're going to FN into that thing, put it in your calculator, and it'll give you 332.965, and this was billion barrels. So what you need to know is if they give you a rate, but they're asking you to find some amount or some quantity of what that rate is changing, then you're just going to integrate the rate, and then yeah, you'll get how much was actually there. All right, so you need to know those. You also need to know the area between two curves. All right, so when you do this, you need to find the intersection points. When they're intersecting curves. When the curves intersect. And a perfect example of that one is the quiz. Number 3. They wanted you to find the area between y equals x cubed plus x squared minus 6x and the curve y equals 6x. Did we give you the picture? We did not. Okay, so you'll have your graphing calculator, I think. I should double check. Pooper scooper. Okay, I'm going to go with yes, you get your calculator, but what we do you? I should have read the PowerPoint just to double check. It looks to me like you do, but we have you do a lot of set it up and then the answer. That's what it looks like. Yeah, so it looks like you'll have your graphing calculator. Okay, so you'll be able to graph these things, but what ends up happening is this picture looks like. The cubic goes something like this. And then the y equals 6x is a straight line with slope 6. So it's just going to kind of go like that. Yeah. So those are the two curves. And if we want the area between the curves, we want this little area there, and we want this little area there. Yeah. And so what we have to do is split this up into two different okay, shoo. For a second there, I gave you the wrong one. Okay. Split it up into two separate integrals, right? We want, so from this point where they're intersecting until this point, you have 6x is above the cubic, yeah? But then from the origin here until you reach this guy, do you see that the cubic is actually on top of or above the straight line? So you always want to go upper minus lower. Yeah, you need to go upper minus lower. So from you got to find the intersection points. Okay, let's do that. Let's find the intersection points first. Okay, so to find the intersection points, you're going to set these two equal, or you could use your graphing calculator, right? You can find the intersection that way. But really, this is actually, I think, a pretty easy. Is it an easy one to do? Hopefully. Set them equal to 0. Subtracting 6x, that'll give you a 12x. There's an x in common. Oh yeah, that factors so nicely. What is that? X plus 4 and x minus 3. Yeah, so your intersection points are going to happen when x is 0, when x is negative 4, and when x is positive 3. So this point right here, you can plug those x's into either one to get the point. This is negative 4 comma, must be negative 24. Plugging it into either equation, the 6x one is the easier one to plug into. This point right here is 3 comma 18, and this point right here is 0, 0. Just so you know, those are the three intersection points. And from when x is negative 4 to when x is 0, your upper curve is oh shit, shoot, sorry. Ooh. I wrote down, I did. Booper, scooper. I drew my cubic the wrong way. Frickety fracketer. Okay. Oh, damn it. Okay, hold on. Sorry, guys. Select. Come on. No, stop. Select. Okay. Let's see if I can get this fixed easily. Actually, no. I'm going to scratch it, and I'm going to... Stop. Now it's flipping out on me. I have no clue what it's doing right now. We're going to do... It's flipping out. Why are you flipping out? Okay. Here we go. We're going to go. Come on. Okay. What I've done so far is right, other than my picture is horrendous. So I'm going to redraw the picture on the next slide. It's a y equals x cubed. It looks like this. Sorry about that. And then going through here and here. Yeah? Okay. I was so close. I just drew my cubic wrong, which will absolutely mess up the whole flippin' thing. It still does intersect here. I had those ones right. Negative 4 and 24. Here at 0, 0. And here at 3, 18. those were my intersection points. Okay. And we're wanting to find the area between the two curves, between that guy and that guy and that guy and that guy. Sorry about drawing that last one. All right, so I'm going to go, now look, from when x is -4 to when x equals 0, the x cubic is above, I know it's blah, 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 the x cubed, blah, 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 is above the 6x function, right? And then from when x is 0 to when x is 3, now you've got this straight line, the 6x function, is above the x cubed one, blah, 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 right? You can think of it as you're drawing a rectangle, your cubic's on top here, the straight line's on bottom here. As you draw a rectangle here, straight line, the 6x is on top, and then the cubic's on the bottom. So that's why we're going to split this up into two separate integrals, where you're going to go from -4 to 0, and then we're going to also go plus and go from 0 to 3. Now from the -4 to 0, your cubic function's above, so we're going to go the x cubed, what was it? It was x cubed plus x squared minus 6x. That was the first function. And then subtract from it the straight line. And then on the second integral, it'll be the straight line, and then subtract from it. Now remember, you're subtracting that whole thing, so I'm just going to add parentheses in there. And that is an x cubed plus x squared minus 6x. All right, so you'll have to do that. And then from there, you're going to be able to just do F and N. So you're going to show me that whole line there. Make sure I set it up right this time, didn't make a mistake. All right, it looks good to me. So that'll be your answer of your setup, right? You'll set it up like that, and then you'll stick it in your calculator, and F and int should have given you an exact answer was 937/12. I did do it by hand though, so that's how I got it. Or it's approximately, which is how you're going to answer on the test, is just give the F and int rounded to 3 decimal places. All right. Robert, what example are you talking about? The one previous? No, I went to 3. If you're rounding, you're going to go to 3 decimal places, unless told otherwise. You should go to 3 decimal places. All right. Was that right, Robert? You're talking about the one before. And I apologize. Okay, good. And I apologize for drawing my stupid graph wrong. Everything else was done right. I just, my cubic, I did it upside down, and then you'd be subtracting wrong. So, okay, so there's that one. Let me know, like, speak up quick if you have questions, because otherwise I'm going to just keep on plowing through and go through to the next example. But if you have ones on specifically these ones, and especially if you find an error that I'm doing, by all means, please, please, please speak up. Okay, otherwise I am going to go on to the next type that you need to know. So you definitely need to know that. Another thing that you'll need to know is something like page 400, number 10. And that one is finding the area of the region enclosed. Area of region enclosed by y equals x squared, x plus y equals 2, and the x-axis. And we did ones like this in class, both I think in the notes, and then this may actually even, yeah, definitely in the notes, right? So the picture of this looks like. And actually in the book it gave it to you. Make you draw it. I think we're going to make you draw them all pretty much, pretty close to all of them. So y equals x squared is going to look like, and it's, I don't know, it looks like that. And then y equals negative x plus 2 is going to look something like that, and then the x-axis. And so you're looking for this area here. That's the area enclosed by all three of them. Yeah. All right. So there's actually two ways to do this. So here's this y equals x squared, and this is, I solved for y equals negative x plus 2 is that straight line. All right. Two ways to do it. Two ways. You could do it with respect to x, and you could do it with respect to y. If you do it with respect to x, then you've got to split this up. You need to partition. Partition them because a good amount of people in here, yay. Partition it because from this point right here, you're going to split it up, right? Because if you're drawing these rectangles with respect to x, means you got vertical rectangles, right? It's just the area under the curve from x squared to the x-axis, right? But then after this intersection point, notice that from here to here, you've got the area underneath this curve of y equals negative x plus 2. So let's figure out where this intersection point is. Again, you'll have your graphing calculator. You could do it that way, or you set each equation equal to each other. The y is equal to each other, so negative x plus 2. And then add the x, subtract the 2. That factors as positive 2 and negative 1, which means these intersect at negative 2 and at positive 1. Did it say anything about? It probably said something about in quadrant 1 also, or something like that. Yeah. Okay, so this point right here is going to be 1, 1 is going to be your intersection point. That's going to be where the two graphs intersect. So that's also where you're going to split it up, right? You're going to write it as the integral from 0 to 1, those are x values, of just the x squared graph, and then plus from 1 till that point must be 2, 0. So from 1 to 2, and this time it's the negative x plus 2. So that's your setup of that guy, and you end up, we'll do fn int, and you end up with 0.833. Keep in mind also, if you wanted to, this is a triangle right there. You could definitely find the area of the triangle for that second guy if you need to. But remember, you could definitely do this analytically, meaning by hand, but you have a lot of setup of problems to do. So that's why we're going to just encourage you, just put it in your calculator, give us an fn int. You're going to set it up and then let your calculator figure out the rest of it. All right, with respect to y, you can actually do it with one integral. And actually, I'm going to go to the next slide for with respect to y, so that way I can draw the picture. So we've got this picture of jut and jut, something like that, right, where this is y equals x squared. We found that that point was 1, 1. We know that is 2, 0, and this was y equals negative x plus 2. Okay, so the second way to do it is with respect to y. And that means when you're doing with respect to y, you're drawing horizontal rectangles. And the reason why you get to just do it once is every horizontal rectangle you draw, you've got this guy on the right and you got this guy on the left on every single one. As you're drawing these rectangles, It's not changing. You're not all of a sudden hitting the other curve or anything like that. And so you're absolutely able to do this with one integral when it's dy. You do need to rewrite these guys in terms of y. So y equals x squared means that x is equal to plus or minus the square root of y. This is only the right-hand side of it, so it's just the positives. You don't include the negative. And then the y equals negative x plus 2. I'm going to solve for x instead, and so I'm going to have a 2 minus y is the second guy. Notice that for when it's dy, you want the rightmost, because that's the bigger x values, minus the leftmost. Bigger, if you just keep in mind bigger minus smaller, right? Bigger minus smaller. Because that's true when it's, when you're drawing your vertical lines. Bigger y, smaller y. Bigger minus smaller, right to left. Right is bigger. X values on the right are bigger than x values on the left. So in this case, your right curve is going to be the 2 minus y, and then the left curve is the rad y. And then keep in mind your limits of integration need to be y values. And so the y values of this guy is you're going from 0 to this y right there. So from 0 to 1 is where you're integrating. So 0 to 1 of that guy, and you're going to just do fn int, and it'll give you the exact same answer. You better get the exact same answer, or else you have done something wrong. So here's the setup, and then the answer there. All right. Type now if you have questions before I move on to another type. Okay. Let's do page 399, number 4. And I'm just going to, they gave you the graph. Yeah. So they give you this graph of these two intersecting parabolas. One of them is opening this way, something like that. I know my graphs are funky. And then the other one is opening that way, something like that. And they want you to find this shaded area in between. They are defined in terms of y's. This guy is 12y squared minus 12y cubed. Oh, so they're not both parabolas. This guy like curves up. Not that it matters. It's not part of our shaded guy. And then this curve here is x equals 2y squared minus 2y. So we've got a parabola and then a cubic intersecting each other like that. All right, so where do they intersect? Did it tell us? On the graph it showed that this is a 1 there. Yeah, so it's intersecting here at 0, 1. Sorry, my graph is so messy. And then again at 0, 0. Those are where it's intersecting. Okay, so it intersects at, and because these guys are, do you see that you must integrate this with respect to y? You've got to. If you try to do it up and down, you're just hitting the one curve, like it's just not even okay. You got to do it this way. And so you're doing it with respect to y, which means you need intersecting y values. So it's intersecting at y equals 0 and then again at y equals 1. And you're able to just set it up as a single integral. It's going to be the rightmost 12y squared minus 12y cubed, and subtract from it the most leftmost curve, 2y squared minus 2y. Yeah, this is the right, and then minus the left, and that's all dy. And then you're integrating from 0 to 1, because those guys will be where they're intersecting. Those are going to be your limits of integration, where they're intersecting. This thing is so hard to write on. Okay. And you're going to so that's your setup, right? You'll write that, and then you'll fn int it, finint, and you'll get 1.333. 3 decimal places, because that's what the AP exam wants. All right. There you go. Talk to me. Type if you have questions before I move on to the next one. No? All right. Let's do page 412, number 39A. And it says the base of a solid is the region of the curve y equals 2 times the rad sine of x. So this is the base of a solid, is the region of that. And the interval is from 0 to pi on the x-axis, and the cross sections are perpendicular to the x-axis are your cross sections are equilateral triangles. All right, so you got this this guy, it looks something like that, and then you're I draw so bad, I apologize, but I should have, there's a better picture in the book. If I draw it just more sideways like this, I can, so let's say it's like that, and then your triangles perpendicular to the base are equilateral triangles. I'm just drawing some. Obviously, that's not all of them. But yeah, so you got this like weird shaped thing, right? Okay, from the x-axis to the curve. Okay, so what you need to do is know what the area of those cross sections are. So in this case, the area of the equilateral triangles is equal to, it's that weird one where it's the side squared times the rad 3 over 4. You can always work it out also. But the sides of this triangle are the height to this curve along the x-axis. And so your S is the 2 rad sine of x. So the area will just be the 2 times the square root of sine of x come on. Sometimes I try to write too fast and then it just, there we go. 2 times sine of x, quantity squared, times rad 3 over 4. And so you end up with that your area ends up being rad 3 sine of x, because your the 2 squared becomes 4, and then the 4's cancel, and so your volume will be in the integral of the area. And so you're going to go rad 3 times sine of x dx, and we're going from, it told us that it was from 0 until right here was pi. So you're going to go from 0 to pi. There's your setup. Yeah, that's what you'll answer as the setup, and then you'll put it into fn int, and you can definitely do this by hand, but Oh crap, I did it by hand. So I don't have an F and int answer. The exact answer is 2 rad 3. And then you can put it in your calculator and check. But so you'll need to do, like, this is exactly what you guys are doing on your, for your projects, right? You've got some base, and then you've got cross sections that are either triangles or semicircles or squares and all of that. So make sure you know the area formulas for, they're in your notes, but I did an example with equilateral triangles. It does not mean that that's what the one you're going to see on the test. You need to know, a circle's area is pi r squared. So that means a semicircle is 1/2 that. What else? A square is side squared. Or if it's the diagonals that are on there, then that is the 1/2 d1, d2. And then a triangle, a normal any triangle is 1/2 base times height, but then the equilateral one is that weird one, which is side squared times rad 3 over 4. Isosceles, I don't think you'll see because I don't think you had any in the homework, right? Because I feel like isosceles, which base are we going to throw as along the base, right? Equilateral, then you know all 3 sides are the same. So you would just use this guy, I guess, if it was isosceles, but I don't think you had that. But anyway, okay, there you go. Volume. So keep in mind, to find the volume, you're going to integrate the area. That's how you found the volume. Okay. The homework on, okay. Problem 11. Oh, on the worksheet. And it's an isosceles. Okay, I'll have to check it out and see. I'm going to keep on going though, because I don't want to run out of time. It depends on what was the base, and then just use 1/2 base times height. You can use Pythag. I don't know. I would work it out, but honestly, I've never memorized this equilateral triangle area. I'll just work it out and figure out what the area is because I can figure out the math of it. But that's just me. I hate memorizing. So, but if you have these guys memorized, you save yourself some work. But okay, let's do solids of that are created by revolving a region around an axis. Got a couple different ones I gotta do for you on this one. Page 435. Number 21. All right, so it says, find the volume of the solid generated by revolving the region enclosed by the parabola y squared equals 4x and the line y equals x, and we're going to do about the x-axis first. Okay, so let's do this. If y squared equals 4x, then that means y is equal to plus or minus square root of 4x, which means that it's 2 rad x and y equals, it's called there. But what does it say? It must say something about it only being in quadrant 1 or something. Revolving the region enclosed. Oh, the region enclosed by this guy. Okay, so here's what our graph looks like. It looks like this, and y equals x looks like that. So that's the little region that's enclosed by it. Technically, it's, sideways, like it's down below also, but the only part that's enclosed by it is this guy, and I don't want to muddy up the waters and draw something else. What I know is this is at 0, 0. This is y equals 2 rad x. This is y equals x. And so that point of intersection right there, you just set these guys equal to each other. 2 rad x equals x. If you square both sides, you get what? 4x equals x squared. You also have your graphing calculator. Okay, so at 4 and at 0. Does that work? Yes, it does. Okay, so 4, 4 is that point right there. All right, when you take this, and we're going to take that shape and we're going to revolve it about the x-axis. So here's the x-axis. We're going to take it and we're going to go whoop to doop and revolve it, which means that it'll look like this-ish, right? Except that, yeah. So it's like this solid, it's like a bowl, but on the inside it's a cone kind of a thing, yeah. And so you do this 2 different ways. You could do it shells or washers. I'm going to choose washers. Do you see that as you slice this, you've got a washer happening there? Yeah. And so for washers, it's going to be with respect to x on this guy. Yeah. You want to do pi times big R squared minus little r squared. And your big R is going to be this distance to there, right? So the 2 rad x is going to be your big R. So big R is the 2 rad x. And then the little r is this radius right there, right? It's just the y equals x. So little r is just x. And so we'll plug those in, and so you'll have pi and then 2 rad x quantity squared minus x squared. And so that will be your volume, will be integrating. I'm going to throw the pi out front, and then it's a 4x minus x squared dx. Your limits of integration, if you have dx over here, then you need x values, and your x values are going from 0 to 4. Yeah. So don't forget limits here. If you got dx, then you should have x values. If you got dy, then you should have y values. Okay. It also works doing shells. I'm going to skip shells though and go on to doing another type that I know my students had an issue with. I'm going to do part C, same problem. So still page 435, number 21C. Because here's the deal. I don't think that we make you use shells. You can confirm that tomorrow. I think it just says set it up, blah, blah, blah. But I don't think anywhere do you have to use shells. If you prefer it, we have the solutions for it, but I don't think that you're actually required to you have to do shells. So, all right, so same shape, right? But this time we're going to revolve it around the line x equals 4. So here was, I'm going to draw this a little bit bigger. Here was my original shape, right? This is the original guy. And remember this was 0, 0. This point right there was 4, 4. And now we're going to take this guy and we're going to revolve it around the line x equals 4. So x equals 4 would be this line right here. That's your axis of rotation. going to take it, I'm going to go wrap it around that, which makes it whoops, that's ugly looking, but something like that, where it's revolved around that way. Yeah, still a bowl, still the cone inside, but wrapped around that way. All right, so here's what you want to do. I'm going to do, you can do washers or shells. I'm going to do washers again. But this time, you do need to do it with respect to y. So show you, here's what, when you do a slice, it's going to be like that is your outer, and then your inner is like that. Yes? So there's your washers. You got to do it with respect to y. Now, how you subtract is you have to do it from the part that is the original, the shaded part. So your right, your most right is the x equals 4 until you reach that guy, and well, that's the smaller radius, and then your bigger radius is going to be from the 4 to the curve over there, if that makes sense. So you got to do these with respect to y, and what were my equations? Our equations were, this guy was y squared equals 4x, and this guy was y equals x, like that. Okay, so you're rotating, even though it's not the y-axis, you're rotating around the line x equals 4, which is parallel to the y-axis. So you're rotating around something that's like the y-axis, which is why you're going to do it with respect to y. Your big R is going to be this yellow one I drew. So it's from x is 4 until minus when x is, I better solve for x, yeah? Let me draw it, put it in a different color. Okay, so if I solve for x, x would equal 1/4 y squared. So that's what the big R will be, from x is 4 until x is 1/4 y squared. So your big R will be 4 minus 1/4 y squared. Your little r is again going to be 4, and then minus, just that spot right there, is going to be 4 minus y. Yeah. And so your volume will be pi times the integral of big R squared minus little r squared. And then this is all dy. Important for, well, yeah, I'll do it right now. Important for you to note that it is not the same as big R minus little r squared is absolutely not the same thing as r squared minus little r squared. No way, no way, no way. So don't you dare go and put parentheses around the whole thing and then square it. It's big R squared and then minus little r squared. Super important. I wrote it as this is big R squared and then minus little r squared, right? That's how you got to write it in there. I pulled the pi out front of the integral. And then you're doing it with respect to y, and so your limits need to be y values. And what are your y values going from? They're going from 0 to, the highest y value is 4, so 0 to 4. And I just set it up. I didn't get an F in int approximation, so there you go. That's how you set it up. Questions on that one before I do a different kind? let's also do page 411, number 7, which is find the volume of the solid generated by revolving this shaded region, which is this straight line. The straight line was x plus 2y equals 2, and it shows that it's intersecting here at 1 and here at 2, and we want this shaded region here, and we want to revolve it, take it and revolve it about the x-axis. All right. All right, so we're going to take this guy and we're going to revolve it about the x-axis. And when you do, then you'll get, why are you not writing? There we go. You'll get that guy there, right? A true cone, right? Our original, though, that's what you got to keep in mind. Your original is this shaded part up there. So on this one, I would definitely do discs for sure. Yeah, it's a solid region. Yeah, you can slice it, and I would definitely do discs for sure. All right, so what is your R? So for each circle, your R is going to be this distance here. Yeah, so let's solve for y. If that's true, then y will equal what, a negative 1/2 x plus 1. Yeah, and so that's actually what your radius will be of each of these circles or discs, right? Is the radius will be negative 1/2 x plus 1. And the area of a circle is pi r squared. And so it's a pi times the negative 1/2 x plus 1 quantity squared. There's your area, and your volume will be the integral of the area. And so we're going to integrate pi times negative 1/2 x plus 1 quantity squared dx. You're doing it dx, and so your limits need to be x values. And they're going from here to here, the x values, so from 0 to 2. And yeah, honestly, I mean, you could do this by hand. We don't want you to on the test, though. We want you to just set it up like that, and then do fn int, and do I have an answer for you? I do not. I do have I have an exact answer for you. It's the exact is 2 pi over 3. And so whatever 2 pi over 3 is what your fn int will give you. Questions on that one? Okay. Don't forget about the length of a curve. Let's do page 420, number 1. We want to find the length of the curve given by y equals x squared from when x is negative 1 until when x is 2. And so the length of the curve is the integral from a to b, which are that's your interval, of the square root of 1 plus dy dx quantity squared. As long as y is a smooth function of x. And sure enough, this guy, y equals x squared, is a parabola. It's a total smooth curve. And especially over from negative 1 to 2, it definitely is. And so what you want to do is find dy dx. And that would be 2x. And so the length of the curve, you're going to integrate it from, they give you the x values, from negative 1 to 2 of the square root of 1 plus 2x quantity squared dx. And there's your setup. I mean, honestly, guys, I would prefer you just leave it like this when it says set up, right? You could make it a 4x squared. But I'll tell you what, like, if you expand it and you get a mistake, make a mistake, I gotta take off a point. So use your, I don't remember, I can't think of the right word for it, but I would be cautious on what I expanded. Yeah, leave it like that. And then especially like on that last one when it was like a binomial squared minus another binomial squared, leave it. Just leave it the way it is and be done with it. Yeah. All right. Then we got some applications, right? And I'm running out of time. So what am I going to give you? I'm going to give you that okay, so applications, you've got work, remember, is the integral when it's not a constant force, right? You're going to integrate from a to b of your force function. Force, keep in mind, is the weight per unit of volume times the volume. Quiz like that, kind of. Okay, you got the regular cylinder. Let's do. Let's do some notes ones. Let's see. Let's do your notes, example 3. Okay, where they give you this conical tank, it's on its apex like that, and 10 is the height, and the radius at the top is 5, and then it's filled to 8. Yeah. All right. So keep in mind that the height and the radius are related, right? So like the radius down here is much smaller than the radius up at the top. So the radius is changing, different from a cylinder like the one on the quiz was straight side. So your radius wasn't changing. In this case, your radius is changing. And so notice that you could do, I don't know. R over 5 is equal to H over 10 is one way to write it. They're proportional, so your R is equal to 1/2 H. That is true down the whole thing. And then what you want to do is you're going to integrate you're integrating these like little, you're going to be doing these little slices, right? You're doing these like little slabs or little slices all the way up until when it's 8. And so your volume, well, really it's like the change in the volume, these little slabs, right, volumes are the volume of they're like little cylinders, so they're pi r squared h, Yeah. But in this case, your radius, or your little guys are 1/2, change it to a y squared. Yeah. And then times your height is like the little dy's or delta y's. Yeah. And so you end up with this change in the volume, depending on which slab you're talking about, right, is pi over 4 y, and then I'm going to change that delta y to a dy when I stick it into my thing, and then into my integral. And then they did give you that the weight, so that's your delta v. So, and then they gave you that the weight of the problem, the thing was 57 pounds per cubic feet. Okay, so the force is going to be this weight, and then this is that change in volume that you're going to plug in there for that force. And then, so the force, let's go to the new slide. So your force is going to be the 57 times the pi over 4 y squared delta y. And then each of those little slabs, the distance is changing, right? Depending on where you are on that slab. It's going to be going all the way up to 10. And so that distance, or displacement maybe is a better way to say it, yeah, it is actually, will be 10 minus y. And so your work is going to be this force and then times this displacement. And so your work is going to be the integral of the 57 times the pi over 4 y squared, that's going to be a dy, I'm going to leave it till the end, times 10 minus y, and then dy, like that. And your limits of integration is always going to be where the stuff is. I know that's a very mathematical term, but it's where the stuff is. Yeah, and so your actual liquid was, right, it was liquid, yeah, oil, is from 0 to 8. And so your integral is going to be from 0 to 8. The limits of integration are always from where the actual stuff is, and then you'll integrate that. So that's how you're going to set that one up. Set it up, and then do we actually have you evaluate it? Yeah, you'll put it in your calculator. Yeah. Yep. So keep it, so the work is going to be the weight, I'll write it out, the weight times the volume times the displacement. Yeah. And then times, really, I should have been using H's. I said R was in terms of H, huh? Whatever. Anyway, DH's would have made more sense. And then keep in mind your limits of integration are where the stuff, I wrote stuff, but in this case it was where the liquid was. It's just that it's not the whole thing. You're getting the going all the way up to the top by doing the 10 minus y part. That's that displacement. The stuff is actually where the limits of integration come in. Where did my paper go? What else was I going to tell you? We are so past time now. Okay. Yeah, think about the displacement, how far it's moving. That's a good way to think of it. Yeah, definitely check out the example in the notes there. And then, what else? I feel like you should also, and I just don't have time for it, but make sure to check out example 2 in the notes from that day. Let me check what lesson that was. Example 2. Example 2 in, really? Okay, yeah. Example 2 in the notes of 8-5 and so this was, and example 7 in the notes on the stats day, which is also 8-5, but it was day 2 or something like that. Shouldn't be, I would just say, in general, the examples in the notes are very good. Don't forget that mu means mean and sigma is your standard deviation. You don't have to memorize the formula, that big old long formula. You don't need to memorize it. You just need to know how to use it and plug it in, which still seems like a struggle. So definitely study the examples in the notes. Okay. I think that was good. Yes, and then you'll see on the PowerPoint tomorrow what all is going to be on there. And I think I did pretty good with matching up examples-ish. I'm not going to say it's 100%. Disclaimer. It's not like I covered every single thing. I'm not going to promise you that, but I think I did a pretty good job. So, all right. I know this is a tough chapter, but you all will do awesome, I'm sure. Okay. Good luck, and I will see you tomorrow. Any questions before I log off? Okay. You're welcome. You are very welcome.